Hey guys. Oh, it sounds so fancy. I need more strings, please. Hey guys. What are we learning tonight? How to turn down some fucking music. And move, I need to move. I have like no space here. Do you see what I just did there? I have no space here. I need my space. Okay, so, hi, I might be a little silent. That might be better. Is that better? Sorry, my voice is a little scratchy. Been a rough day. So let's see, who's in here? I'm thinking that's earlier. We got Cot. What's up, Ka? Pocket size. Jesus. Dope intro, thank you. And Rec, we got you in here. FPS Glenn with the war cries. Talk science to you. Oh, I'll talk so much science to you tonight, baby. You don't even know. Spider-Ham, what's good? Pyro, how's it going? Dodgy? Don't pour Pluto me. No. You have no more brains left to melt? Yes, you do. I'm sad. I thought you were doing a cosmetology stream. No, Cosmology. I would never instruct you on how to put on makeup. I'm not really good at it myself. Yeah, so this music's about to get super intense. We're just not going to do that. No. We're going to just bring up my Spotify over here. We're going to move this over here, and we're just going to do some good music. Let's see here. Take me on a trip. Universal wisdom. Oh, I'll take you on a trip. We're going way back. We're going back to, well, actually, we'll be talking about the expansion of the universe, cosmology, so the beginning of the universe. Then we're going to be talking about dark energy and dark matter and how they play in the role of such things. Dark energy is the repulsive force, so it pushes things, whereas dark matter attracts things. Each have a part to play in all this stuff. Tim is 5'9". Tim, how tall are you? Wulati, what's good, buddy? And Barrick, hey. Is this the real sky? Yeah. We're good. I think. I'm from East London. I don't know what fancy is. You call cookies biscuits. That's really fucking fancy. It's okay because space is expanding. Right. It's expanding into itself. Mind already blown. Dr. A just subscribed. You guys are subscribing, and I don't know where my alerts are. They're not making sounds. Oh, because they're not on this screen. Derp. Hey, Doctor, thank you for that subscription, buddy. Welcome back. 4 months. Cannot stay, sadly. So here's another sub, whatever. You'll catch this. This will be on the YouTube, the interview portion, and also on here. But I'm going to export the interview portion to YouTube. Very good to see you as well. Let's see. Definitely not 5'9". Gotcha. Tim is 5'9", just subscribed with Twitch Prime. Thank you so much for that. I appreciate that. You haven't even seen the space shit, or have you? All I know is that you're 5'9", your name is probably Tim. Thank you so much for that support. You have no idea what that means. Are you blushing because your cheeks are turning red? A little bit. I haven't streamed like at my computer in a while. It's been a while. Tot, how you doing? See, Tot even just said, how's it going? It's been a while. I know. It has. Thank you so much, Tim, for that sub. I appreciate it. You guys have just seen me like out and about and drinking. I just look like I'm just. we're gonna tone those down because I don't want people to think that's all I do. The few times I changed my username is all. Well, I like your new username a lot. Yeah, that's what my next question was going to be. What did it used to be? But you don't have to answer that. Halo music, yeah, it's the best. Except, when Bungie decided to fire the guy. Do you guys remember hearing about that? Akara, hey you. My day was a day. I had a pretty bad day, but it's okay. We got space tonight, guys, and that's what always makes me feel better. I got my cheesecake, some coconuts for you, and boy, am I ready to go get Science Star. I love this so much. It's great. It was Aero Engineer. Oh, okay. You want to hear about your bad day? I care. No, I don't want to talk about my bad day. It's really fucking bad. But it's all good. Everything will be good. So yeah, so tonight, probably here in about, actually pretty soon here, we're going to have Dr. Jason Steffen on. If you guys don't know who he is, he does stream on Twitch and he does more. So you guys won't hear me swear. You guys, just so you know, don't freak out. I'm still here, but when I talk to people in education, I typically zip it. As far as, just because this is stuff that goes on YouTube and I don't want to disrespect them. So, there's Horizon Science. Yeah, there you go. Horizon Sci. So he has his own Twitch stream and, he gets a little bit more educational stuff. Like he's a teacher. Okay. He's an astrophysics, teacher at UNLV. So that's the University of Nevada, Las Vegas. I've been going through papers and stuff today, so holy shit, that's true. Everything is I love space. Yeah, so tonight we're going to be talking about the wow, see, this is what happens after when trying to do space. Yeah, just cosmology, so the beginning of the universe. And there's several different theories for how the universe started. The leading theory is the Big Bang theory. And then also what comes after that. So what can we actually see? What is the observable universe versus the non-observable universe? So what we can see is 13.82 billion years back with the observable universe. And we'll talk about the cosmic microwave background radiation, all that fun stuff. Guitar physics hero. I think that would be good too. So what do you think about the theory that dark matter could be gravitational signature? Could be the gravitational signature of matter in nearby parallel universes. See, and see, I honestly, I just stick to what we're. I don't really theorize. So I just stick to kind of what I do know. I'm boring like that. You can ask these questions. So I'm gonna get in an interview with him. Probably shortly. I need to check my Discord. Let's go ahead and go to this. But he's actually going to go on Google Talk with me. So there's a party. I always have that party happen. Every single time. Every single time. So we're going to be talking about this. A lot of this. You have the cosmic microwave background radiation chilling back here. And what's funny is we can't see past that, but we are aware that that's roughly about 400,000 years after the birth of the universe. So, but there's a bunch of leading, there's only one leading theory, but there's a bunch of theories regarding this kind of stuff. So it gets a little weird, and don't worry, if you guys have questions, you guys can ask them during the interview. If it doesn't get answered and you want to ask it again after, we usually take time for questions, and then I can talk to you guys after that, because I usually have to exorcise the demons. So, hey Atomic, and hey Matt. I took a cosmology course for no credits while in college for fun. Shit hurt my brain. Yeah, that's what I'm saying. Like tonight, guys, it's gonna be one of the heavier streams. That sounds horrible. I feel like I just walked into a Tampax commercial, but it's gonna be a mind-bending stream when we start talking about how photons travel in the expansion of the universe, and that what you see takes time to travel to you, and then you have to factor in the expansion of the universe. It's kind of crazy. Are you an astronomer, mate? No, I graduated in computer science, but it's a hobby. A hobby that consumes me. Fernando, you are so beautiful to me, haha. Do you like how I said that? That's how I read it in my head. I put an accent there and everything. Natural. You guys and your names. I hate you. Mr. Potato Head, how's it going? With Future Man. Do photons wear backpacks or carry stuff in pockets? I don't think so. I don't think they're even aware of themselves. Although that'd be super cool. Yeah, the CMBR, a mad bore, you know. You acronymed that. Nashra. Yeah. So, we're going to be talking with him about that kind of stuff. I'm going to wait to see if he's emailing me on anything. Oh, I need to get in my email. Hi, derp. But yeah, it's going to be a little mind-bendy. He might use a little bit of technical terms. If you guys don't understand anything that he is saying, be like, I don't understand it. Because there is a chance that I might not understand it, but if I don't understand it, I'm likely going to ask. But still, there is really no stupid questions. I spy Horizon Psi. He could write a kid's book lightly on the self-aware photon. See, that would be awesome. And I do spy him too. There he is. There he is. So that's Dr. Steffen. You guys can actually, I think we have, do we have the guest command still up? We do. Yeah, there he is. So there's all his info. Sweet. I win. I win. Hey, JW. How's it going? Naaman, save me, please. I can't deal with Twitch gamers tonight. Well, we're going to talk about space. If that's okay with you, Naamans. I'm pretty sure it's not okay, huh? So I'm ready whenever you are, Dr. Steffen. I'm on the G chat. We're going to be testing the video thing. So you guys are our guinea pigs. Or we are your guinea pigs. Whichever way you want to see it. I'm here. Is everyone behaving tonight? Yeah, tonight's okay. It's those other IRL streams. Although, I'm sure we get some fun stuff when we talk about astronomy in here. Preparing to have my mind blown. And also, in case anybody doesn't know, if you're going to TwitchCon, we have a panel at TwitchCon, so I'll be talking on a panel for education on Twitch. Me and Dr. Steffen. For that sites. Everybody but JW. I keep calling him Jwin. I think I just need to stick with that. I don't want to convert. Is your panel streamed? I'd love to watch it. It probably will be. I wouldn't imagine that it wouldn't be. Maybe it won't be. We're going to get all the details on that. You know, they haven't sent out the schedules yet, I don't think. But basically, like, it's all done. They just have to put it in the schedule. Hey, Wistasa. I was just thinking about you today. Sorry, working on the Hangout. Forgot that Firefox has trouble. Why are you on Firefox? Oh. Okay, hold on. Un momento, por favor. Hold on. Answer. Hi. You probably can't see me. Oh, because my webcam's being taken up. That's fine. You don't need to see me. You can see me elsewhere. So hold on. Let me try to capture this window.
Hey.
Can you hear me?
I can hear you, yeah.
Okay. And you guys can probably hear him.
I can hear you twice.
Oh, gosh. You don't want to hear me twice. So let's see.
Yeah, I can hear you.
All right. Good. I'm going to move this over here, and I'm actually going to... I'm just capturing this monitor. I'm being lazy with it right now. But what I can do is I can also... This is Doctor... He's bigger than me. He's bigger... I'm going to make your camera bigger than mine. Everybody's going to love that. Hold on, let me fix this. You're good. Can everybody see him? Hopefully you can see a bunch of... Let me move me over here too.
So I tried a new thing this morning. I went all the way to a 1.
You went all the way to a 1. I can see that there's a difference there. There is a difference. I was going to say. We can just work with that. How does it feel?
It's actually quite a bit cooler than
I would think
both
so.
like more cooler and also cooler temperature wise than
Awesome.
it is with a tube.
Is it really hot there right now?
It was actually kind of chilly today. It was down in the low 90s.
Oh, yeah, because in the low 90s, is that what you said?
Yeah,
Yeah, I know.
it rained, and we also had a big water spill in our building, so the rooms flooded.
Oh, yeah, no, it was pretty cool here, and not being sarcastic. It was actually cool here recently. So, like yesterday, I think it was like 70, which of course, after, really hot temperatures, that feels significantly cooler. All right. So I was already telling them about kind of what we're going to talk about. Do you see what's on my screen right now? Just a really, not a complex thing to describe it all.
Uh-huh. Yeah, I see that. I also have, should we choose to use it, a set of slides that we can go through.
Oh, yeah.
That deal with like the universe composition. And if you're up for it, I have a test audience participation survey.
Ooh.
So
guys, we are getting technical. I'm all about it.
Because we want to, when we go to TwitchCon, if we can get even a 1% slice of the 2.5 million people that tuned in last year.
1%'s good.
Yeah, 25,000 people watching us.
Mm-hmm.
If that would be a 1% slice. So that would be
right. That's
so we can test out some of the technology that see if it works.
And you guys can all hear this. If you guys don't know who he is, hey Galvatron, how you doing, buddy? Type guest, which I'm sure Joe did it. Whatever, Joe. Whatever. Hi, Joe. Low 90s, so cold. Yeah, so this is Dr. Steffen. He's a professor at UNLV. And am I saying it right? I'm saying astrophysics, but you're kind of like an astronomy/physics. Like you do kind of,
all my background is in physics, okay. So all my degrees are in physics and math. Okay. And I kind of view myself as a physicist.
Yeah, I would say so.
Does astronomy.
Yeah.
But to some extent, I'm like a chameleon in that I can change what I am to best make the case to my audience.
Right. So physicist sounds. I don't know. I think it sounds fancier than saying astrophysics. But same thing. I mean, he works more on the study of the small, which would be the quantum. Right? Am I right with that?
Yeah. So. At least in the past, I've done quite a bit of research into things like dark matter and dark energy, gravitation, stuff like that.
Gravitational waves, stuff like that?
Yeah, well, so the gravity research that I did, I never quite got into gravity waves, although I kind of skirted around the edges of it a lot. The research that I did was on testing looking for new forces that were gravitational strength in the couplings. Also testing whether gravity behaves the way that it's supposed to. So there's a thing called the equivalence principle, which is that two objects falling will fall at the same rate regardless of what they're made out of. And that need not be true. Mm-hmm. And so there are ways that you can test the equivalence principle. And I was involved in some tests of that.
Gotcha. Okay, so that all makes sense. And then there's, you guys, we talked about this just like briefly last time, but I love talking about it because it is kind of cool. He did, Wired Magazine interviewed him on how to board a plane. And that's one of the things that's really cool about him. And I'll link some of this. Anything that you guys see on my screen is going to be linked in the VOD description. So I will be putting this on YouTube, and that will be, I know there might be a little bit of background noise, but he's actually in his office right now. And you're right next to a flight place, aren't you?
Yeah, the university and the Las Vegas airport share a corner. And so the airplanes fly directly over campus.
Yeah, that's like, Las Vegas has, Reno and Las Vegas. Or, sorry, Nevada has Reno and Las Vegas. That's pretty much all there is.
Yeah, those are the two places. And Las Vegas historically was the little sister. That's why Clark County, where Las Vegas is located, is like the size of New Jersey. And because nobody lived here when they divided the state up into counties.
Right. Yeah, no, I've been to one little thing called Burning Man, but we're not going to talk about that. So, but that's a city that builds itself and then goes away. I did it before it was really trendy, though. So now it's like super trendy.
It's like going to the first Lollapalooza.
Exactly. It's like this is actually when it was still had its Woodstockiness, and now it's not at all. Now it's I don't know. They raffle tickets and stuff. It's really weird, but yeah. So if you want to send me on Discord or Discord, you could send me the slides, and I can put them up over here if we want to do that.
Another alternative would be for me to do this, and
oh yeah, you can screen share. I don't know how tiny it's going to be because I made you tiny and I made me tiny, and then I made this. We'll see. We can test it. We can guinea pig it. This is what this is all about. Okay, hipster Sky. Thanks, Wistesso. Oh no, that's good. I think I can actually make that bigger now.
So we'll see. And if this doesn't work, then
no, it actually does.
Then I can share.
I think actually that's pretty good. Can you guys see that? Everybody in the community. And Bachi, welcome back. Bachi the bartender, thank you for that sub.
If I shrink this, it will take up more of the screen.
And Bachi's a tier 3 sub. He's one of my only tier 3 subs. I think Bachi's like 2 of my tier 3s. 2 out of 3. Thank you, Bachi. Thank you so much, buddy. All right. No, that looks good. Can you guys see that okay? It's visible. Can you guys kind of see what the wording says, or do I need to make it? If I do this. Because I can actually, what I can do, hold on. I can put this down here.
So I should say congratulations, by the way.
Oh, thank you for the degree. Is that what you're referencing?
Yeah.
Thank you. And there's an airplane taking off for me, too. Thank you so much. I appreciate that.
So actually, I did talk a little bit about how airplanes fly earlier this week because it's part of the class that I'll be teaching this fall. And I have since had a discussion with another of the physicists here who's actually looked into it a bit more. And at some point, I'll need to do the full story behind how airplanes fly because there's actually a lot to it, including when they say, "Oh, all these people died because of pilot error," like what the typical pilot error is.
What is the typical pilot error? I'm just thinking hanging back, maybe flirting with the flight attendants.
No, it actually comes from because it's fairly rare that an airplane will stall. Like, why do airplanes fall out of the sky? It's fairly rare when they stall. The issue is that when you're flying along, you'll have some angle of attack, like your airplane's coming in at some angle, and the challenge, if you're at the optimum, where you get the optimum lift, is that if your nose points downwards, then you'll get less lift and you'll start to fall. And if your nose points further upwards, then you get less lift and you start to fall.
So it's
the correct way to respond to that is to go into a dive. The natural way to respond to that is to pull back on the stick and make it even worse.
So it's almost like that reaction when you're sliding in on like ice and with your car. You actually want to turn your wheel into the direction that it's spinning.
Yeah. And you don't want to slam on the brake. You want to pump the brake.
Yeah.
So that your wheels can turn. And so, like, the natural reaction is exactly the wrong thing to do. And so, and there's been some cases where they've recovered, like, the voice box, and there'll be, like, one pilot trying to push the plane into a dive like he's supposed to, and another pilot is like, I don't know what's happening. I'm pulling back as hard as I can.
Yeah. So typical pilot error, chat says. Typical pilot error. Yeah, no, that's kind of crazy though. Great. Well, I'm not flying anytime soon, so I think we're good.
Yeah, I'm gonna. Anyways, that's a different thing. So
no, that's good.
This the picture that I have up here is a rough understanding of the composition of the universe, kind of rounded to the nearest 5%. That only a small fraction of the universe is regular matter, like protons,
like us,
neutrons, electrons.
Like us. We're regular
us
matter.
And stars. And the truth is that even a smaller fraction is made up in stars and planets. The majority of the regular matter is hot gas.
That's what everybody says I'm made of.
Yep.
Yeah.
So, Chicago windbags, which is actually what the Windy City was named after, was the politicians and not
the actual wind. Right. A lot of people don't know that. Hey, guys, did you write that down? That's important. Chicago's not named after its wind. It's actually a political thing. Okay. Heard it here first.
And so the amount of regular matter that's in kind of a condensed form is closer to like 0.5% or something like that, or like 1%. And the rest of it is just this diffuse gas that's out in between galaxies and in galaxy clusters and stuff. And then about a quarter of the matter in the universe is dark matter. And then the remainder, which is just over 2/3 of the stuff in the universe, is dark energy. And dark energy wasn't discovered until fairly recently. I remember when I was an undergraduate, which wasn't that long ago. I guess it's
don't even do the math. I was gonna say this is dangerous. Don't do it.
So I could probably walk to the parking space where I was pulling into the parking lot when the discovery of dark energy was announced, and I was thinking, wow, these guys really don't know what they're talking about, because everybody knows that dark energy, like there's no cosmological constant. That was kind of what was proposed. But it was a real thing, and there's been several different ways of confirming its existence, and all of those, they've all given kind of a consistent story. And even today there was this result. I know.
I have it. Did you see it in my Discord?
I did.
And that was Dodgy. That's all Dodgy's fault with the BBC when I have that up here. So we can look at that one together, because I kind of want that was on point. Dodgy, you were on point with some space news. Hey, Gooch, how's it going?
It's really good timing.
Yeah.
And they have, I missed it yesterday. They live streamed kind of not really a press release or press conference, but the effective press conference where they had someone giving a presentation about the first results from the dark energy survey. When I was at Fermilab, they were building the camera. In fact, the guy in the office next to mine was the guy whose his sole job for the dark energy, he had several responsibilities, but his sole job for the dark energy survey was shipping the camera from the United States to Chile, and making sure that it passed customs and that it made it on the ship okay, and that it was transported, like it had the rig that it was put on had enough wheels so that it wouldn't get shaken to pieces. And so I was there during the time that they were putting it together and having a lot of the initial science meetings. And then, so it was good to see, the first results coming from it. It's supposed to be basically a 5-year survey, but it'll probably go longer than that once it's shaken down and stuff.
Mm-hmm. Very, very. So so regular matter, and just because I really like to convey this to everybody in here, like, we're just going to go ahead and make it kind of, I don't know, we're regular matter, guys, pretty much. Now, we're saying that there's, the stuff that makes up planets and stuff like that, which would be kind of what we are made up of too, to certain planets. Well, I mean, well, we won't even. I'm gonna start tearing this apart. So we're regular matter, guys. Then that's just gonna make you feel really good about your life. No, I'm kidding.
We're just regular.
We're just regular matter. We don't get to be any of the dark matter or the dark energy. And hi, Quasar. Real quick, I just got a donation. I'm sure it says less than 3. No, it says hot gas. That's not even fair, Reloads. That's not even fair. Thank you for the $5, buddy. I appreciate that. Perfect sign language. Thank you. I was like, I think I'm backwards. I don't know if that's a less than 3, but I did it for you. Quasar, how's it going? And Bobby is Bab. Hey, Bab. So guys, just so you know, I'm still here. You guys can ask questions. He's looking at the chat too. But if there's questions that we miss, we are going to have like a little section at the end. Just so I know, Dr. Steffen, what's your time like?
I think if we did this for an hour.
Do you have a little bit longer? Because it's probably.
Oh, and then I can stick around.
Okay.
Yeah. So.
Okay.
Like we can do like the heavy hitting stuff for an hour to an hour and 20 or 30 minutes or so, and then that'll give us a little bit more time for questions than we've had in the past.
Yeah, and then we can also. Well, actually, I'll just let you say it because I've already posted this in the Discord, I think, but I didn't make the tweet about it yet. Do you want to tell them the news that we have coming up with Tabby Star?
Yeah. So. Tabitha Boyajian She was at Yale, now she's at LSU. She's the discoverer of Tabby star out of the Kepler data. She's also one of the main drivers behind the planethunters.org. And she we'll be having kind of a three-way discussion in like a week, 10 days.
Yep. So it'll be on August 14th, and it looks like we're scheduled for 6 p.m. Mountain Daylight Time. So if you guys know anything about Tabby Star, this is going to be the woman that actually discovered it, like he said. I mean, I fangirl. You guys don't even know. This is what gets me excited when I meet scientists and people that have made contributions. So I'm excited. And you guys probably know about it too. I know a lot of you guys probably do. Hey, Kilgren, when you're the 5% but still considered regular. I know.
We're the star-bellied sneeches, I guess.
Yeah. So let's go ahead. So now you guys know I will be tweeting that out. If you're part of my Discord, I will keep reminding you guys. August 14th, 6 p.m. Mountain Daylight Time. We're going to have her on here, and you guys can ask all of your things. A lot of the, you guys probably know about it, the fake news stuff with like the Dyson sphere. Well, not the Dyson sphere, actually the megastructure. That kind of came from Tabby Star. That really gave it didn't come from that, but it gave that a huge kick because they don't. Yeah.
We could actually invite the guy who proposed the alien megastructures. I know him.
Oh my gosh. Let's totally do that. I know. Okay, my chat would love this.
So he's a very good scientist.
Well, yeah.
The proposal for the alien megastructures was basically a parenthetical comment at the end of a paper that investigated a lot of very realistic situations.
Right. It was like a mention.
That's what people ran with.
Yeah, it was a mention. It was a brief mentioning. Because, in science, guys, we do actually have to consider aliens. We do. If we're going to mention all of the possibilities out there, yeah. But I remember I actually read that paper not even about 2.5 weeks ago. And it's a brief mentioning. But yeah, it's a star. Just a brief synopsis. It's a star that dims. It doesn't have any real, I guess you could say, symmetry in its dimming. It's very weird. Sometimes it can dim by 2% for a few days, or actually, yeah, a couple days, and then go dim by 20% for weeks. And there's really no. You can't look at a chart of the activity of its dimming and say, oh, well, yeah, no, this is going to start dimming around this time.
Yeah, I can explain that. Yeah, it's not an easy thing to do.
Yeah, go for it.
So
yeah, we'll be talking about that, and that will be really fun. I'm so excited. So we're going to have a lot of this kind of stuff coming up. Hi, Solitary.
So if I may,
go ahead.
So that I don't get too deep into this and then have to back out.
Right.
I want to try this experiment real quick. It's only 2 questions. So if everyone is ready, and then we'll come back to the dark matter stuff.
Is everybody ready?
This way we can get it over with, and we don't have to interrupt something when the discussion picks up.
Okay.
So I'm going to share a different screen.
His face.
You can share my face to start with.
There's his face.
And then I'm going to share this.
Everybody in here is born ready. What is this? What's this all about?
It's my Woody Harrelson.
It was a good one. Wait, so how do these? I've never actually scanned one of these. Don't yell at me.
So, and I also have a.
How do you scan this? Oh man, go find.
I can share a link through. I can share a link too. Let me put the link up.
Felmal, thank you for your subscription from downstairs. By the way, it was Felmal's birthday, everybody. My roommate's birthday was yesterday, so he's going to hate me for saying that. Go ahead and let me give you a permit. Actually, one of my mods can.
So I just need to make sure that I'm pulling the right thing up.
I don't even know how to scan these things, guys. It's a Groupon code.
You point your phone at it and it works. And
really? Just like point it at it?
If you have the app for it.
I don't have the app for it. I'm a woman of
okay,
minimal
here we go.
apps.
Here's the link.
I have Jupiter on my phone, though. There's the link. Okay. So this is
a
survey?
I'm gonna, for those who've used the QR code, it's going to come down and I'm going to pull up and it's got 2 questions. And I want to see if we can both get lots of answers and if we can show in real time like what the results are.
Yeah, we can.
And there's a JavaScripting thing with Google Forms. I've not written in JavaScript. Have you written in JavaScript before?
Mm-hmm. Yep.
I might rely on your expertise to make it so that we can take results and then populate a new question based on those results.
Yeah.
But I've never.
I took one class in JavaScript and like PHP stuff, but we'll
figure it out. Anyways.
Yeah.
I needed to do something. Oh, that was this. I needed to open up.
Dark matter. Yeah, so everybody, if you want to fill that out, well, okay, hold on.
I mean, it should take just seconds to fill it out.
And guys, I'll get to those subs in a second. I just want to finish oh, wow, computer science. Okay, so I did that. Let me check the subs real quick while everybody's doing that. Bloody Clam, thank you. Back for 4 months, Bloody Clam. Thank you so much, buddy. And Alice, SMC love, guys. SMC love. Alice, thank you so much for that sub. And Filmal, thank you again. Alice, welcome. Welcome to the dark side of the universe. This is where we discuss all the space stuff. That's my stream. I'm really boring. Not really. It's pretty cool. I'm a little biased.
So we have 10 responses.
10 responses. Come on, guys.
So far.
Spam that. I'm going to spam the thing again. Here, guys. Go and fill out the survey. You guys, we're doing stuff on Twitch. Come on.
This is practice for our panel so that we can interact with the audience.
Mm-hmm.
And so the questions may be kind of similar, but so I need to pull something else up.
Thank you for loving science. Thank you for loving science. And again, if you guys don't know who this is Dr. Steffen. If you type in !point guest, you'll get all the information. Hey, Lycan and Rec, thank you for that host. Lycan, how you doing, bud? What is this? What is this? Oh, he's posting it again. Lycan, thank you. You're amazing.
So that's what our results look like.
Let me make this bigger. I can barely. Okay, even with that, like
nobody likes the sun.
No, the sun's really boring. Even though it's not.
Well, but like solar coronal mass ejections and
coronal mass ejections, those CMEs. You guys want to know about those solar flares and the magnetic?
How the sun shines and solar neutrinos and everything.
Yeah, and those magnetic field lines. Come on.
Black holes did pretty well.
I was gonna say. So here's my guess. My guess was black holes. I'm surprised exoplanets didn't get picked up. I thought exoplanets would. Look at how many people want physics. You guys are all biased. I'm just calling you out right now because this is a space stream. Everybody's like, I want more physics in my life, please. That's awesome. So yeah,
so this seems to work.
21 responses. It looks like it's updating real time though.
Yeah, it does. It updates every time someone clicks.
Wow. Nice, guys. Engineering would be sweet. In history, philosophy, we need a debate channel, like a legitimate debate channel. You just couldn't have people be very sensitive. People would have to walk in there and. So it sounds like it sounds like World War III over there, guys. He's just next to a place where planes are constantly flying over. So just
let me. Oh, let's see. I think this is the only microphone I can hook up. So.
Well, if you want to turn down the mic volume, I can hear you pretty well, and I can turn you up here. Let's try that out just to see if that will actually do something. What microphone are you using? Is it just like a...
It's my cell phone.
Oh, yeah, no, it's not. It's funny. It sounds
Let me try plugging in my regular... Because I have a microphone with a little fluffy thing on the top of it.
It would be, oh my gosh, pop screen type stuff.
Well,
I don't even know what I'm trying. The fluffy bit.
Okay, so let me know in. Let's see. Then I can do this.
Every channel is a debate channel. True, that's true. We're gonna let him he's gonna test this out for us. I'm biased. I responded with what I studied for my MS. That's fine, Muffins. You're good. Don't open that door lightly. What door? If there was a debate channel, I think they'd have to have really good moderators, but because that stuff would be absolutely nuts, right?
So this is my other microphone. Is that better?
Hold on, let me wait for this. Renaj, thank you so much for that host, buddy. I think it is actually. We have to wait. We have to wait for a plane to fly over. Is there a plane flying over?
Not yet, but Las Vegas is open 24 hours a day. I mean,
it sounds pretty much.
So it
sounds the same. But we'll just wait for a plane to fly over, and if so, then you can just adjust the volume a little bit, and we can tweak that if it's a big problem. It might not be. Chat might not even. What's this guy doing? Okay, so, anyways,
yeah. Okay, so this worked. I think this will be I think this is something we can work properly.
Yeah, so a lot of people want physics, and if you guys want physics, I'm plugging his channel again. He does talk about this stuff. His channel. Hey, Hammy. Hey, you.
And airplane now.
Yeah, so that's still loud. So let's try turning in your mic volume. Let me know. Let me know. If you go to your playback, or I'm sorry, your recording devices, right click over it and do levels. I usually use decibels, but you can just use the slider thingy.
Okay, let's see, input volume. I think it'll probably show up one way or the other.
Yeah, so it will, but it could, I mean, it's more the gain is what I would say that is, but we can just test it a little bit.
Okay.
Let me hear you be like testing as you're turning it down.
So this is I'm about 3/4 of the way down.
That's good, actually. I think that will substantially help. Because then I can turn down.
There.
Yeah, perfect.
And now I can go back to so now that we did it, I think
we're good.
Test over. Thanks everyone for indulging me on this. We can.
Wait, can I see the results one more time? Wait, scroll up again. So guys, this is what we just did. Wow. So black holes. Wait, whoa! Cosmology is beating out black holes.
Yeah, because black holes are kind of.
I know they're not really that interesting, but everybody thinks they're super cool just because they're weird.
Space-time was in there, so space-time is interesting.
Space-time's really weird. Because we're going to talk about a little bit of that today. A little bit, sort of, kind of. It's space-time continuum.
And down here.
Physics got 24. We got a bunch of science nerds up in here. It's awesome. But history, it looks like history did well. And then computer science, engineering and philosophy. That's pretty cool. Nobody wants literature.
Well,
sorry.
Yeah.
I mean,
so I have. I should show this. Well, maybe I shouldn't show this, but I'm going to do it anyways.
You're fine.
So I recommend to everyone to read a lot. I actually have a.
Oh, I know exactly what you're going to show. Is it the same book?
No.
Okay.
Well, there's that, but also these are the books that I've read since starting graduate school. And it's been a while. It's been further than it used
read
to be.
Stuff and Chops. I was waiting for it. He's like, you guys should read. I've been trying to get them to read. They're not going to read. People don't do that anymore. It's okay. I don't blame them. I really don't.
These are the books that I've read in the last, I guess, 20 years, most of them at least.
Just a small list. Nothing, no big deal. I listen to audiobooks. That counts. Yeah, so
because audiobooks are the easiest way to do this, especially when you have a large.
And Universal Wisdom's like book recommendations?
Yeah, there are some. Like this one right here. It's called The Discovery of France. It's the most interesting book I think that I've ever read.
Discovery of France? Of Francia?
And At Home is another one that's really interesting. It's by Bill Bryson. Endurance, about the Shackleton expedition, was really interesting.
Yeah. No, I've read that one. Shackleton's story is actually really interesting. So yeah, there's a lot. There's a lot of books. This guy's read a lot of books, guys. He's got.
So when I said literature, this is kind of what I had in mind.
I think some people try to do book readings and like things like that. I'm sure some people in here
but
maybe.
readings isn't quite as interesting as like if you had like a real discussion. Here's the things that I thought was
History of pi.
coming in having assumed that some of it's been read.
I kind of want that list actually.
I can share the link.
Yeah.
I can share the link with you later.
Hey, Flames. Yeah, no, if you want to share it with me and then I can put it somewhere else and then share it with them, I could put it in my Discord and we can have it as a pinned message.
It gets longer because when I listen to books, I listen to it at about twice the normal speed because otherwise it's hard to concentrate. It's too easy to get distracted.
Okay, I gotcha. Okay. Yeah, so,
all right, so
everybody's digging that, by the way. Post it in Discord. Everybody is totally digging that. Yeah, so I can get it from him and I can move it. I can export it to a different document. So it's in case he doesn't want any of his personal stuff shared or anything. I don't mind you guys. I get personal. All right, so you guys saw that there was a lot of dark matter, less than dark energy. Mostly the universe is dark energy, and we're just ordinary matter. Now moving on. Okay, take the stage.
Yeah. So the early universe is kind of a tale of two glues. Where one glue is significantly stronger than the other glue. And there are a bunch of particles from the early universe that form from, there's a bunch of leftover stuff after matter-antimatter annihilation. The fact that there's matter in the universe, we don't actually know why there's matter in the universe, why there's excess matter in the universe. Because most of the physical processes that we understand would produce matter and antimatter in equal quantities. And so the fact that the universe is made out of matter and not antimatter, or that there aren't equal amounts of matter and antimatter, is still an unknown thing. We can explain something like half of the difference, but not the whole thing.
Right.
So we have extra matter. That matter likes to interact with each other, and there are two forces in particular that are important for our early universe. One of them is the strong nuclear force, and so that's the force that sticks protons and neutrons together and allows the nucleons to stick together to form heavier and heavier atoms. So initially, the universe, if it's just made out of protons and neutrons, you could only form hydrogen, and eventually neutrons only live for about 10 minutes before they'll spontaneously decay and turn into hydrogen.
Right. And then you start getting into, we're not even going into the proton-to-proton chain yet, though, right?
Right. So this is different than the proton-proton chain.
Right.
This is
although
many of the
simple.
Many of the processes are the same. It's just this is happening not inside a star. It's happening inside a star that's the size of the whole universe at early times. So as the universe is expanding and cooling off, the interactions will evolve with time. So early on, the things are hitting together so violently that. Okay, so strong nuclear force, and the other one's the electromagnetic force, and we'll talk about that later.
Yeah, so hold on real quick. Let me just real quick. Let me see.
Mayhem as the particles are flying by each other at very high speeds, and the collisions are so violent that it's not possible for any of the glues to hold things together. So whenever the particles come close together, they just bounce off of each other. But as the universe expands and cools, eventually the particles slow down to the point where the stronger glue can stick together, while the weaker glue still is not capable of holding together because of the collisions. And during this period of time where the strong glue is effective, but the weaker glue is not, you form heavier nuclei beyond just hydrogen. And the two most common ones are deuterium, which is hydrogen with an extra neutron in it, and helium, which is helium is two protons and two neutrons. You can also have helium-3, which is two protons and one neutron.
Right. And deuterium, a lot of people, is everybody kind of hearing this? I'm sure that a lot of people, this is pretty dense stuff, but you can just understand about the interacting things we're dealing with here, like deuterium, helium, and then we're probably going to get into some hydrogen, I'm guessing.
So the hydrogen is already there from the beginning.
Oh, right. That's going to be the first one created. Never mind.
And
Just
so
joking.
then you're building things up by throwing a bunch of ping pong balls into the room that have a little bit of sticky tape on them.
Right.
And those that stick together are forming these heavier and heavier elements.
Mm-hmm.
And if there's a lot of matter in the universe, then this kind of nucleosynthesis will go on for a long time. You'll keep building lots and lots of heavier things, and you'll get more and more of them. So if there's a lot of stuff in the universe, you'll produce a lot of deuterium, you'll produce a lot of helium, you'll start producing a lot of lithium, the lithium you can add stuff to the lithium and get boron and carbon and so forth. You can build your way up. But as the universe is expanding, the particles are getting farther and farther apart. And eventually you get to the point where it takes longer than 10 minutes for the neutron to find a dance partner.
Right.
And once it takes longer than 10 minutes for the neutron to connect with something, it will spontaneously decay and you run out of neutrons. Like all the neutrons will vanish.
So if I can I
there's
interject?
only a small window in the early universe where you simultaneously have collisions that are tame enough to allow particles to stick together, and collisions are frequent enough to preserve the neutrons before they spontaneously decay.
Right, and that's what I was actually going to say. Like, is that this is a pretty violent thing?
Yeah, very violent.
Very violent.
If you were to assign a temperature to it,
very hot, guys, real hot.
Let's see, it's 2 MeV versus 2. It's a million. It's around like 100,000 Kelvin. No, I lied. That's wrong.
I'm sorry, sir. Can you please do the
it's
Fahrenheit
around
conversion?
1,000,000 Kelvin or 1,000,000 degrees. So it's warmer than your typical summer day in Las Vegas.
Right. So yeah, but so right. Okay. I'll let you go because there is something I want to talk about like this because you're talking about how they're able to linger longer and that allowed them to scatter. And when I'm saying I'm actually talking about some of the particles that were created at this time. There was a scattering that happened, but that might be actually later because you're still just going through the nucleosynthesis portion of this, right?
Right.
So we'll get to that, guys. But if this is a little bit dense, don't worry. This stuff you guys don't, I mean, this is super cool, interesting stuff. And this is what he talks about a lot on his stream. But we're going to get to the stuff you guys might understand a little bit more. Just bear with it. Just don't give up. Don't give up.
Great. So the idea is by measuring the amount of deuterium and helium and carbon, or deuterium, lithium, helium-3, helium-4, by measuring the amount of this stuff that we see in the universe, we can actually pinpoint how much matter there was in the early universe. And so the graph that's here, the main thing about this graph is that we can measure each one of these things. So each line corresponds to a different chemical species. And the horizontal lines correspond to the actual observations of the amount of these different things that we see. And deuterium is the most telling one. Basically, if the universe had a lot more matter in it, then we would get more deuterium. And if the universe had a lot less matter in it, well, if the universe had a lot more matter in it, then eventually that deuterium will get consumed in the production of lithium and carbon and so forth. Mm-hmm. And if the universe has a lot less matter in it, then we would have a lot of deuterium and a lot of helium-3 left over. So by measuring these amounts, we can actually pinpoint the density of regular matter in the early universe. And that ends up being what this vertical line is. And that vertical line is where we get, so by measuring each of these species, we say, where does it all agree? And it all agrees at about 5%. And that's how we get this 5% slice in this figure comes from the fact that we can measure the relative abundances of the elements, the light elements in the universe. So that it's a good question for someone to ask, like, how do we know that that's how much matter there is in the universe? And that's the reason why, is that we can go out and we can observe these light elements and we understand the nuclear processes that go into producing them. So that's that 5% is the regular matter. Eventually, the universe cools down.
Wait. So I can interject here now because I know that I'm going to talk about the scattering because that's why, I mean, things started cooling down. But it cooled down and also lost its density too. The universe did, didn't it?
The universe cooled down and did what?
It lost its density.
Yeah, it cooled down and spread out.
Yeah, it spread out. So it started scattering because at that point, when we're talking about the birth of the universe and all these things starting to happen and ignite, you have really hot temperatures and it's really violent. There's not really a lot of place for these things to move around. So they're crashing into each other. So you have like protons, electrons, and neutrons. And after those things, and they're not in that order. They're not created in that order, guys. But they were constantly interacting, right?
Yeah. So they're always interacting, and it's early on, especially because the collisions are so violent, they're just scattering off each other. I mean, it's like dogs and cats living together, mass hysteria.
Mm-hmm. Mm-hmm.
And then as the universe cools and expands, it becomes more pleasant of an environment. The nucleons can stick together, protons and neutrons can stick together and build these light elements, complex nuclei like helium and deuterium and stuff. So that's the regular matter that we see. This slide that's up here now.
Well, regular matter meaning we start seeing photons.
So regular matter is protons,
neutrons.
It's like the chemicals.
Right. Okay.
Basically.
Okay.
So we'll get into. It was much later that we start seeing the cosmic microwave background.
Like 400,000 years later, right? Yeah. Roughly. Okay.
So the dark matter, there's a lot of evidence for dark matter, and the original evidence for dark matter came from looking at clusters of galaxies, like the one that's shown here. But also, we can measure directly the mass in dark matter in these clusters of galaxies because of the way they distort light that comes from distant sources that are past them. So if you have a very distant source, as the light from that distant source comes towards us, it will get bent by the gravitational influence of intervening galaxies. And so when you look at this picture, there's a lot of arcs. So I'll flip back and forth between these. There's a lot of kind of lines that form circles around the large galaxy cluster. And the amount of mass needed to distort the shapes of these distant objects by this amount is much more than the amount of mass that can be seen in the stars themselves.
Mm-hmm.
And so most of the mass in this cluster of galaxies has to be some form of dark matter. You can't explain it just with the regular matter that we see.
Right. And
so that's one example of evidence for dark matter. And there's a handful of others, like the way galaxies rotate.
Well, yeah, I showed this before. Here's how gravitational lensing works, just so you guys can see that again. I'm going to leave that one up, though, too. So That's what he's talking about. You're here. You're trying to look at something back here. And whatever is the stuff that's in the middle there that can have, it can be, I mean, that's how we also detect black holes, right? There's some of that, like how it actually distorts the light in between, the pathway in between.
Mm-hmm.
So, okay, anyways, go on. We'll get to, well, we already talked about that. You guys can go to the previous VOD. Come on now. Okay, go on.
Okay, so that's one example of evidence for dark matter. Another way that we know that dark matter exists is because galaxies and how they clump together is a consequence of the gravitational interaction. So if you start with stuff that's uniformly spread out, let's see if this works. Go. So you can see that there's small regions that are slightly overdense, and those will collapse under their own gravity and start to form galaxies and clusters of galaxies. And so as we look back in time, because light doesn't travel instantaneously from one place to another, as we look farther and farther away, we're looking at the universe as it was older, like more and more in the distant past. And so by studying how galaxies are grouped together as a function of distance from us, we can look back at how galaxies form with time. And in order to get the growth of galaxies and galaxy clusters that we observe, you also have to have dark matter. So this is another example of how dark matter plays a role in forming, in the formation of kind of the structures of the universe.
Right. Actually, that's really cool. And they've done, like, you guys, we saw this in one of the documentaries that we watched on here. They have supercomputers. I'm using old terminology, but they've recreated this, and you can actually see it. I forgot who it was. Someone in my chat said it kind of looks like neural pathways, or I don't even know.
Like a neural network.
Yeah, it kind of does, like the structure,
like
the filaments and stuff. Yeah, it's pretty cool. That's actually really cool.
So we can study. We can understand the amount of dark matter by looking at lensing. So that's this galaxy distortion, the distortion that comes from gravitation, the gravitational influence of dark matter. We can understand the amount of dark matter based upon the growth of structure. And we can see, so here's an example. This is the predecessor of the Dark Energy Survey, whose results just came out, who had some results that came out today. This is the galaxy clustering properties from the Sloan Digital Sky Survey. So each dot in this figure is a galaxy. And as you go back in time, which is that redshift, so that's basically going back in time, and it's going back in time to about half the age of the universe almost. Then studying how these galaxies are grouped together, you can piece together how much gravitation, like attractive gravitational influence, does there need to be in order to explain this?
Which we would say dark matter.
Yeah, and it has to be dark matter because we already know how much regular matter there is because we measured it from Big Bang nucleosynthesis, from the light elements. So then dark energy is the third piece of the pie, and that was discovered. The work to discover it was done in the 1990s, and the initial announcements came out in 1998 with two groups of teams, one from Australia and one from Berkeley.
Are these the
when
two
I say
guys?
They came from Berkeley. The leader was at Berkeley, but there were 100 or so people that were distributed on the science team working on it together. And in particular, there was a very hardworking graduate student who did most of the hard work analyzing the data from this particular survey, and that was Adam Rees. That he was the third recipient of the Nobel Prize when the Dark Energy Nobel Prize was awarded.
Now, real quick, are these the two competing science teams that were trying to explain the expansion?
Yeah, so they came out with results at the same time, and they both agreed with each other.
Yeah, it was Geek Wars.
Basically, the leader of the two groups, and then Adam.
That's awesome. So you guys, we talked about that too. There was one of them actually believed it was the expansion of the universe was slowing down, and then I don't know if the other one believed it was accelerating. But they were independent groups doing this, and they came up with the same numbers. That's pretty awesome. Okay, go on. Sorry.
Yeah, and it's been, and ever since then, there's been an increasing. They've looked at more and more data, and the story has become more and more consistent, and including this, the Dark Energy Survey. The Dark Energy Survey is not doing this same kind of science, this particular kind of science to measure dark energy, but it has other probes that measure it. So what we're seeing in this particular image is a galaxy. Typical galaxy has about 300 billion stars in it.
No big deal.
And there's one star that's particularly bright down in the lower left corner of the image. And that's a supernova. That's a star that's exploding. And in particular, it's a white dwarf star that's exploding. So it's basically the sun in the distant future will eventually, the core will shine so brightly on our sun that it will blow off the outer layers of the sun's atmosphere, and eventually you'll just be left with a core. And that's the white dwarf star, is the leftover core of a star that shone too brightly that the gravity wasn't able to keep its upper layers of atmosphere on.
And that's when you get those those really lovely planetary nebulae, is from the outer regions of the sun when it dies. But so that's what we're seeing right there. You guys, we're looking at our sun's future, that really bright star chilling at the bottom.
That's our
future.
Star at the bottom.
Is that what you're talking about? Or am I wrong?
that the sun will become a star like that.
Right.
If you add mass to it, eventually that core would become unstable and explode. And that's what we're seeing, is the explosion of a core left over from a star that's roughly the mass of the sun.
Gotcha. Roger that.
And so that particular star is comparable in brightness to the entire galaxy. So you have one star that's exploding. And this is a very violent explosion. This isn't, when a star goes, like when the sun gets to the end of its lifetime and becomes a planetary nebula, it does so kind of slowly over a period of many hundreds of thousands of years. When it explodes like this, it does it in like a quarter of a second and just completely
collapses in on itself, right?
And when it does, it outshines the galaxy. So this brightness that you're seeing with this one star that's similar in brightness to these 300 billion stars in the rest of the galaxy, that's only 1% of the energy that's given off by that star. 99% of the energy that comes off of a supernova comes off in the form of particles, like particularly neutrinos. So most of the energy is coming off in neutrinos. So in terms of total energy output, the exploding white dwarf star that's 1.5 times the mass of the sun in this case is giving off almost 100 times the amount of energy as the whole galaxy put together.
Yeah, so our sun's going to be reduced down to the size of Earth when it dies and becomes a white dwarf star.
So what they did for this particular survey was, because this particular type of supernova, it's called a type 1a supernova. The nomenclature isn't important other than to know that they all come from the same type of star and they all happen at the same mass. And so that allows the astronomers to calibrate how bright they are, because they're all the same properties. They have the same composition, they have the same mass, so they should have intrinsically the same luminosity. They should be equally bright. So when you're looking at these supernova in more and more distant galaxies, you can reconstruct how the light from these distant stars is spreading out. So if you're looking at a candle on the surface of the Earth, you can tell how far away you are from that candle based upon how dim it gets as you move it away. And I have a picture, I think. Yeah, okay. So if you have a source, the light's going to spread out, and it will become more and more dim the farther away that source is. Basically because all the light that leaves the surface has to leave another surface at a different distance, and surface area goes as 1 over r squared, or surface area goes as the square of the distance.
Right. So you're talking about redshifting. Redshifting, right? This is redshifting.
This is not redshifting here. This is just the spreading out of the light waves.
Okay, so the dimming. Okay, the
redshifting comes in a little bit later.
Okay.
So this is just the total number of photons as they leave, they spread out. Now, if the universe is changing shape as these photons try to spread out, if the universe is changing shape, then they will also be dragged along by the universe. And so you get this image. So you have a distant supernova. The one on the left is if you have a collapsing universe where the universe was expanding in the past and then is coming back together and is eventually going to recollide, then what that means is that very distant supernova will have gotten dimmer. Supernova, as you go farther and farther away, will become dimmer and dimmer and dimmer up to a point after which they become brighter and brighter and brighter again. So that if you're looking at a supernova that's at the beginning of the universe's lifetime, and you're seeing it at the end of the universe's lifetime, it will be just as bright as outshining 300 billion stars. Because all of the light that left it, if the universe is collapsing on itself, is going to come back in and hit you at the end of, as the universe collapses in on itself. Because all the photons that left have to come back in as the universe collapses. So it's a way of measuring how, if you look at supernova as you go farther and farther away, the brightness will change based upon whether the universe is expanding, contracting, or in this case, accelerating its expansion. And so when you look at the brightness of the supernova in our universe where we actually live, they saw that it had a shape that looked like the image on the far right. The supernova were getting dimmer faster the farther away you went, which meant that that the farther back you look, the more dim they became than you would predict from just a constant expansion rate.
Right, and it actually looks like it scatters even more so, more exaggerated, the funnel at the top.
And that was the direct evidence that the universe was accelerating in its expansion. It's not just moving along at some constant rate, but in fact, that the rate of expansion is getting larger and larger as time goes on.
As time goes on, yeah. So it's actually, guys, it's exponentially increasing in its expansion. So that's important to know. And actually, Albino Ghost has a really good question, and I'm going to get to that because we're going to talk about that. Like, what is space actually expanding into? These are actually really good questions, but we'll get to those because I can chirp up a little bit during these times. Like, this is the stuff that I have no qualifications to talk about. That's why we have Dr. Steffen on here. So good questions.
So
keep them, save them because I want those asked. Those are good ones. Okay, sorry.
Yeah, no problem. So these are the original data that showed that the universe was living on the left side of this plot, which is basically if you get expansion and then reacceleration. And that was the discovery of dark energy. So now, so going back to our story of the glue, the universe has cooled, and eventually we have the electrons that are bound with the electromagnetic force to the protons, and those, once the universe has cooled to the point where they can stick together, they're going to emit light, kind of as they fall to their final resting spot in the atoms. They're going to emit light that is going to follow the expansion of the universe, and as the universe expands, it's going to stretch the wavelength of that light out. So, you start with collisions that are too violent for the electrons to stick to the atoms. So the universe is basically ionized.
Mm-hmm.
And then when the universe cools to the right temperature, the electrons will bind with the atoms and they emit a single photon that goes with that. And that single photon expands as the universe expands, and starts as like in the ultraviolet, but as the universe expands and stretches out the wavelength, we observe it today in the microwave. And so that is what gives us the cosmic microwave background.
Right. And it was a constant interaction, that was happening at this point. And we can pretty much just go ahead and say that it's like in equilibrium together, right?
Right. So initially there's an equilibrium between, you kind of assume a chemical equilibrium
mm-hmm.
at all times, but as the temperature drops, what that equilibrium is will change.
Mm-hmm.
And eventually you get a phase transition where basically the universe goes from being, it's almost like the universe went from being a gas to a liquid or a liquid to a solid. It went from being a plasma, like an opaque, the universe was opaque at the time. Photons couldn't escape because they kept bumping into things. And then when you bind electrons into atoms, then the universe all of a sudden becomes transparent and all these photons can stream outwards.
Now, just so everybody knows, photons are light. That's what we see with we actually see only a certain part of the electromagnetic spectrum. That's the visible portion. This is microwave. So this is actually lower frequency. But yeah, so exactly what you're saying right there is that photons couldn't escape at some point, but then they were absorbed and then they were sent back out again. Photons were, readmitted again. And you can correct me if I'm wrong on that, but that's kind of how that worked for a while, at least.
So just at the last stage, the electron, when the electron goes from being unbound to being bound, it gives off a photon, or it emits light. And once the atom becomes bound, it's also transparent to most other. So the reason that air is transparent is because it's not ionized. There's not free electrons going around. There's not free electric charges.
Mm-hmm.
If you do have freely flowing electric charges, then the atmosphere would be opaque. So, for example, when a lightning bolt strikes, the reason that you can't see through the lightning bolt is because when the lightning bolt strikes, the temperature becomes large enough that it strips an electron off, and now you have free charges. So any photon that's coming towards it, any light that comes into it, is going to interact with that charged particle.
Mm-hmm.
When you bind something into a neutral atom, it no longer is able to just interact with any kind of light that's out there.
Right. So at some point, the photons were able to travel freely. They were able to fly around freely. We had light flying around freely, and then without getting reabsorbed. And then we got this nice little pretty shell.
Right. And then 13 billion years later,
right.
That light's been stretched out so that it's now in the microwave spectrum.
13.8 minus 400,000.
Is happening at the time that these initial photons are emitted. You're going to have some regions of the universe, because the universe is pretty dense at the time. You can have sound waves propagating through it, and those sound waves are going to be, there's going to be some regions where there's more stuff and some regions where there's less stuff, which means that there's going to be some regions that are slightly higher in temperature and some regions that are slightly lower in temperature. And those are going to be imprinted on the photons or on the light that streams out at that time. And so when we look at the cosmic microwave background radiation, we can look for small changes in the temperature of the light that's coming from different parts of the sky. And that's what this image shows, are temperature variations. These temperature variations are 1/1000th of 1% variations, 1/1000th of 1% of a degree variations in temperature.
Yeah. Okay. So universalism's like mind reaching over. Like, you're just looking at temperatures. That's don't worry about this. This is at the point which we can see. This is about 13.82 billion years. This is minus 400,000, which accounts for after the Big Bang. So this is looking at our universe is pretty much being like hours old, right? I don't know.
This is basically
putting
a
it in
faded baby picture of the universe at age 400,000 years.
Mm-hmm. So this is a baby picture.
So for those who remember or who play retro games on a CRT machine, so like a television that existed from the 1950s until like 1999,
aka furniture.
A fraction of the fuzz that you would see on the screen, like the snow, was the cosmic microwave background radiation. And when your radio dial is not, for those who have a dial, is not tuned to a radio station, a fraction of the noise that you hear is actually the universe speaking to you.
And that's how they found the cosmic microwave background radiation, right? They had a big radio dish, and they heard this static, right?
Yeah, they heard a static, and they tried everything to get rid of it.
Yeah, they were like, "What? This is annoying. Get it away."
So it had seams in the side. So this was at Bell Labs in New Jersey. It had seams in the side because they put it together with big metal plates. And so they put in some metallic tape to cover the seams. They shoot out a bunch of pigeons that lived there. They cleaned all the pigeon leftovers out of the thing, and they couldn't get rid of this noise that they saw, the static that they saw. And so they talked with people just down the street at Princeton and said, and there was a group at Princeton that was actively looking for this very signal. And so they contacted the group at Princeton and says, "We have this noise in our antenna and we don't know where it's coming from. Do you have any idea what's going on?" And the response from the people at Princeton was, "Well, we just got scooped because they discovered the thing we were looking for." One of my graduate advisors was a graduate student of the guy at Princeton who was looking for this.
Sorry, chat's being funny about the pigeons. It's making me laugh.
And believe me, we have pigeons. Some people call them flying rats. Some people call them doves.
Brutal.
They don't know what they're talking about.
Yeah, doves, no. Mm-mm.
So one of the things with the cosmic microwave background is that it can tell you what the overall energy density is of the universe. And basically it does it in the following way. If you have let's see if I go this way. Okay. That's not really what I want to show. I don't unfortunately have the picture that I want to show up.
I have a bunch of these because you're going to pretty much have to, because I have some really cool ones that I want you to talk about and give your input on.
Okay. So if you have a sphere, like if you draw a triangle on the surface of the Earth,
oh God,
the angles actually don't add up to 180 degrees.
I know what you're getting into now. Okay.
So if you take a piece of paper and you draw a triangle, the angles add up to 180 degrees. But if you take a sphere and draw a triangle on it, the angles add up to more than 180 degrees. If you take a saddle and you draw a triangle on it, the angles will add up to less than 180 degrees.
Mm-hmm.
And so this cosmic microwave background, what you can do is draw triangles that connect the bright spots and the dark spots and do an analysis that says, what are the angles in these bright spots and dark spots? And do these angles add up to 180 degrees or more or less? And if the angles add up to more than 180 degrees, then it says that the universe is curved in a way that it will eventually close on itself, that the universe in the very distant future will collapse on itself. And
AKA the big crunch. Is that what you're talking about?
This is the big crunch. It means that there's so much matter in the universe that it pulls everything back together and the universe will self-annihilate.
This is a theory, guys.
If the angles that you draw between these light and dark spots on the sky add up to less than 180 degrees, then it implies that that there's there's relatively little matter in the universe, and the universe will expand forever without bound. If, on the other hand, the angles of these triangles add up to exactly 180 degrees, then that tells you that the universe is flat, meaning that it behaves the way that you do geometry on a piece of paper.
Right.
And if that is the case, then it tells you the sum of the regular matter, the dark matter, and the dark energy together. So we have evidence for the amount of regular matter that there is. We know that there's dark matter,
mm-hmm.
and we know that there's dark energy from each of these different observational things. We know from the supernova results that there's dark energy. We know from the dark matter results from the observations of galaxy clusters that there's dark matter. And we know from Big Bang nucleosynthesis that there's regular matter and how much there is. And with the cosmic microwave background radiation, we know what the sum of those pieces are. And that's how we get to that pie chart. So when you add these different things together, you get this figure that's up here, where the cosmic microwave background basically tells you that the universe is flat. That's why the large ellipse, the large orange ellipse, is almost on top of the flat of the universe. We have the supernova results that tell you about dark energy, and you have the growth of structure, which is this baryonic-Houtzig oscillations. That's the dark matter. So
these
are
all very good. Can you just say these are good? These are good words for dating, guys. You guys have to write all of these words down and just say them to the lady, or for like the 3 females that might be in here. This is
just whip it out of your wallet. Say, hey, I got something to show you.
Yeah, can you say that last one? You were describing. You were like, this is just a hyper. You were going into that. Can you say that last? The green sounded really fancy.
The green is the measurement of the total matter in the universe.
Okay, that doesn't sound as fancy. You had some. You kind of like had it.
And so the green is almost vertical, and so it pinpoints basically the total matter. That's the x-axis. The horizontal axis is the total amount of matter. The vertical axis is the total amount of dark energy, and the sum of them being 1 is this flat, the line that says flat on it.
Gotcha.
So you can see the cosmic microwave background, which is the orange thing, is almost on top of the flat. That's how we know that the sum is equal to 1. The green one is the growth of structure and the formation of galaxy clusters. That tells us the regular matter. And the supernova results, that's the blue, that corresponds to what's the total amount of dark energy. And all these completely different measurements, I mean, yeah, they use telescopes, but they have completely different systematic uncertainties and everything. They all cross at one point. Mm-hmm. That tells us that there's, that's where we get the 25% dark matter, 5% regular matter, 70% dark energy.
There you go. Boom, guys. No big deal. Real easy. You could do it in your sleep. Okay. That's actually really interesting, though.
And there you go.
There's those filament things again. That's that web, that cosmic web.
So that's basically how we know, when someone shows you a picture, oh, here's how we know that there's dark matter. We know that there's dark matter and that there's dark energy. this is how we know. We know the sum, and we know that each part exists, and we can estimate the fraction of each part based upon these different kinds of observations.
Mm-hmm. We're going to get into like what about regular energy, like regular energy meaning like regular matter. Is that what you mean, Mad Republican? But we'll get into that because I have my own little slides here that he'll be able to just touch on lightly. We'll get through it.
Okay, let me give you the football.
Oh, are you passing it?
Yeah.
All right, I'm going long.
So I'm gonna have a big picture of me.
Yeah. This is what your college professor does. He just sits here in the dark. Let me move this.
I usually turn the light off because in the daytime, if I have the light on, then you get a big glow up in my forehead.
His head reflects, guys. Hey, it's just photons. You can see them. It's part of the visible. So I'm going to put him, because I actually have to adjust everything real quick.
And I keep rubbing my head because I'm not used to having hair. I've never had hair this short since I was.
Yeah, no, it's like the invisible beard. When men shave their beards, they keep doing like this gesture for at least a week or two. I've seen it a few times on Twitch. Thank you, Twitch, for showing me that. I appreciate it. The more you know. So what we'll do is we'll put you here, and then it can be right there. Yeah, so we were talking kind of lightly about this. So you guys can see here's the cosmic microwave background radiation. It's just a heat signature, but it's what we can see. Actually, it's 13.82 billion years back into time. So about roughly when the universe was about 400,000 years old. So that's pretty significant and substantial. Now we have this dark ages thing, and that's what we were talking about with those photons getting absorbed, right? Is that what the dark ages would be?
So the dark ages is the interval between when the photons were emitted at the time of recombination. So when atoms became neutral and emitted kind of their last gasp, and the formation of the first stars.
Okay. Yeah. And then so we have our first star about 400 million years after the universe was born. Right? I mean, that's what it's saying
and
here.
Those stars had a completely different chemical composition than the stars that we have today.
And that's what's super cool is we can tell through spectroscopy what their chemical composition is, and we can be like, those are, would we call those first-gen stars?
Yeah, and in fact, with these ones, so they'd kind of be population 3 stars is the technical term.
Technical, right.
But we don't really understand what these stars would look like because, for example, we don't know what the maximum mass that they would have is. They could be as massive as like 1,000 solar masses. Where today, with the current chemical composition of our own galaxy, where our stars that are forming in our neighborhood, they can only be about 100 solar masses as their maximum mass. So some of these early stars could be up to 10 times more massive than the most massive stars that are allowed by today's chemical composition.
Gotcha. And would that just be because of the abundance of material that was around at that time?
The main reason is that heavy elements, like when I say heavy elements, I mean elements heavier than helium. So stuff like calcium and iron, they're all more opaque than hydrogen.
Right.
And so when you have opaque stuff that's settling in on a star, the light coming from the center of the star trying to get outwards is going to hit the stuff that's opaque and bounce off of it. And it's going to actually it causes an increase in pressure inside the star. And so if you try to put more material onto the star, that pressure will push that material away. And so the bound that you get on what's the most massive star you can form is based upon, if you try to add more stuff, the pressure from the radiation leaving the star is going to drive it away instead of allowing it. It overcomes gravity and doesn't allow it to collapse.
Gotcha. Okay. Yeah. So that's hydrostatic equilibrium.
Yeah.
Yeah.
And so there is a picture of a star that is simultaneously trying to form and trying to die at the same time. I guess simultaneously doing it at the same time is the same thing. It's Eta Carina.
Oh, yeah. And I can show people that in Space Engine after this. I can show you actually, yeah, because I always say it wrong. They said Carina in one of the documentaries.
You say Karina, I say Karina.
I've heard Sharon, Karen, Sharon. I'm hearing all kinds of things with space names. So
I call it Karen.
it's Sharon.
Um,
But it's no, like it's funny though. So yeah, we have the Dark Ages, and then we have the first stars being born, and things were pretty compact, as you can see. Like things were pretty closely, close relatively than they are now. And then the development of galaxies and planets. Now the Hubble, we talked about the Hubble before. Hubble was able to look at a lot of these, galaxies that were pretty far away. But with the James Webb Telescope, we'll be able to look back further to some of these baby galaxies. Now, what's crazy about it is they're old. They're very, very old, but since time or light takes time, am I saying this right? Light takes time to travel to us. These are not in their current state. We're seeing them as they were. So we're seeing back in time when we look that far back into the universe. That's a little bit of a mind bend, but a lot of people understand that. When you're looking up at the stars at night, you're not seeing light that's being emitted. Real time, you're seeing that light that emitted, however many light years it is away. If it's 7 light years away, you're seeing 7-year-old light.
Right.
So, but from...
So light travels at about a foot per nanosecond. And so a nanosecond is 1 clock cycle on a 1 gigahertz processor.
Now we speak in my language. Okay.
So and this is actually important for computer science.
Yeah.
For like the development of computers going forward, is that if you have a 10 gigahertz processor, then light can only travel about 1 inch per clock cycle.
You have no idea how much I love my string.
If you have a microprocessor
it's amazing.
That's made out of something where light can't travel across the microprocessor in the amount of time of a single clock cycle, then you have synchronicity problems. You can't have synchronous operations across the microchip because the information can't propagate across the chip in a single clock cycle.
Yeah, and so what's really weird is that the universe, like we haven't really discussed the structure and the shape, but the shape is what's cool about it, without going too much into that because that's its own thing, is when you look out, you'll see. Let's say the universe is a sphere, which people go back and forth on what they think. I think they've concluded maybe it might be. Maybe
so the visible universe is spherical because that's
right.
We can see in all directions.
Yeah, so that's what's cool.
The universe itself is flat.
Right.
And because of dark energy, the stuff in the universe, the amount of stuff we can see in the universe is actually getting smaller.
Right.
Because the most distant objects, as space is expanding faster than light can propagate through it.
Right. Did you guys hear that? So that's a big thing.
The most distant objects are actually moving out of our horizon.
Mm-hmm. So what happens is like you will see a different sphere. When you look out, you'll see a different sphere, but it's always coming from the same time, pretty much. And it's going to be the same size sphere all around. There is no center of our universe. We don't have a center. Although I'm pretty sure humans would love to say that we do, but we don't. And these are kind of weird concepts. But so to talk about the expansion, okay, this is the stuff that's really gonna kind of blow people's minds. But and you and I have talked about it briefly when you and I were talking about other things regarding Twitch and stuff. But okay, so when you're looking back and what we can see, 13.82 billion years back, that's the observable universe. That's not the age of the universe itself. And also what he's saying is that the expansion of the universe is accelerating, and that number is increasing. Its acceleration is increasing with the acceleration. So it gets a little bit more complicated than saying, okay, well, we can only see 13.82 billion years. You're actually looking at things where I think, and I could be wrong with my numbers, but I think it's something like 42 billion years for the radius. And if we want to get the diameter, it's like 94
so
billion.
That's actually not something that I know about. Like I know redshift and the age of the universe. The actual map between redshift and age is not something that I mean, I could look it up, but that would, I know the people to ask to get that answer.
Right. So, well, right. So what I'm trying to say is I've been thinking of a way to say it.
Like, what's the actual
Well,
radius
if you have a
if you were to
photon,
measure it now with a large ruler?
well, if we were looking at a photon, we were observing a photon, that was, let's say, um, I'm trying to think of how to say it. It's a photon that's been traveling from its own perspective like 10 billion years, right? And then it would have to travel the distance. And this is where I don't want to botch this. It'd have to, so the way light actually would have to travel, it has to account for the expansion.
Right. And the way it does that is that as the universe is expanding, the light gets stretched out.
Mm-hmm.
And so it loses energy as the universe expands. So the visible universe, what we can see in the universe, is, you have 13.7 billion light years, or 13.7 billion years. Light has propagated through most of that time.
Mm-hmm.
But there has been expansion since that time that has driven galaxies farther and farther away from each other.
Right. So the object would actually be around like 47 billion light years then, if we account for that.
That sounds plausible. I don't actually know the number, but
yeah, I'm thinking that's it, because that would be the radius, and then if you take that, then you get 94, if I'm doing the math right, which I think I am. But yeah, it's really difficult to talk about. So and this is when I show my fancy rubber band about how space is created and how galaxies move, guys. And you guys have seen me do this before. But like, if we say that each of these tick marks are galaxies, and the expansion of space is accounted for when you stretch it, it's not necessarily that the galaxies are moving away from each other. It's that the space in between is being created. So when people talk about the expansion of space, some people say like, well, what is it expanding into? And I think what would be, it's expanding into itself pretty much, right? It's creating itself, sort of, kind of.
So I don't know that anyone really knows what. So
it's like still part of the universe.
The system is growing.
Uh-huh.
So there's a little bit of kind of metaphysics into what is space-time actually. Is it really a physical thing, or is it just a coordinate system that we have placed on the universe? You don't have to have a real fabric, like you don't have to have a real substance, and in order to explain what we see. Like even with gravity waves is a distortion in the coordinate system that comes from things spiraling inwards. So in terms of like, what does space actually mean? I think there are many completely viable interpretations of what space means and what space-time is as a physical entity. And I think the least amount of assumptions would be that it's basically nothing except for a coordinate system that can be distorted by the presence of energy.
Yeah. And then when people want to start talking about like what's outside of the universe, that's when you get into a whole bunch of interesting stuff. But yeah, no, I think that was actually one of the things I wanted to talk about. I know there's a lot of really good questions, and I don't want to, but I think what I was trying to convey kind of came out in that, what we were talking about there with the 47 billion figure that I was saying, if there's light, traveling in and of itself, and it's from its vantage point, would it have to travel, through the observable universe? And then you get some weirder numbers. But let me see what other pictures I had here, because I brought these up, and some of these guys I can actually watch with you guys. I just wanted, here's the theories of universe creation. So is it agreed that the Big Bang is like the leading theory right now on how the universe?
So the Big Bang is a class of models that start with a hot, dense collection of stuff that grows and expands and cools with time. So that, as a paradigm, as like an overarching model of how the universe works, that is the accepted version. Now, what actually causes this initial kind of explosion or creation of material. That's where different Big Bang models would differentiate themselves.
Gotcha. Yeah, because it
So there's
looks like
one
you see these here, right?
from Paul Steinhardt that's called the epchirotic universe, where there's that our universe lives on a 4-dimensional subspace of a higher dimensional thing, and then when these higher dimensional things bounce off of each other, it creates a new Big Bang.
They get pretty complex. There's even at the very end here, we've got flat hologram.
Yeah,
or that
and
we
there's
live in a
also like the
digital.
holographic universe, which is the idea that since it comes from some theories about black holes, where if you form a black hole, that all of the quantum information that goes in from the material that goes into forming the black hole can be written on the surface of the black hole if you write with a small enough pencil. And
I just had the it's from what's the, I can't even think of it, the Hans Zimmer music from Interstellar. It just like went through my headphones, but yeah. So it's written on the black hole. These things are always like people talk about multiverse. You can explain that if you can. I'm sure you can.
So there's several. Again, and this one is on the list of books that I had. It's a book by Max Tegmark called The Mathematical Universe. A lot of the stuff I agree with and thought was well reasoned. Some of it I thought, okay, this is just out there. But the idea of a multiverse is that there is basically, does there exist stuff beyond what we can see? And I think there's different levels of how much is there beyond what we can see. One of them is there
airplanes? Is there airplanes?
Come land for a second.
Are there airplanes that we cannot see?
So one of them is, can you imagine going, if you were to go to the edge of our current visible universe, would there be a galaxy just beyond it?
Mm-hmm.
If so, then that would be outside of our visible universe and would be part of this multiverse, meaning that it's a part of a visible universe to something else, but it basically comes from the same structure. It just happens to be over our horizon. That's like saying, is there California, even though I can't see California because it's over the horizon? And so that kind of multiverse, I think, is totally plausible.
Mm-hmm.
Now, there's other theories that people put forward, like, well, what if every cosmological parameter is completely random, and so you have an infinite number of universes, and they all have some number, like some different cosmological parameter mixture, and so we happen to live in one where life can form. That's where it starts getting into metaphysics that I'm.
Yeah, that's where it starts to get a little crazy, and a lot of these things.
I mean, there's serious scientists that are doing. That are thinking of this. It's not that they're misguided or anything necessarily.
No, isn't that what they work on? Like
they're
at the
getting
perimeter?
into a realm. They're following the math into realms where we can't really test it.
Mm-hmm. Right, and yeah, because science doesn't really take us there yet. Let's see. So I think I've got the yeah.
So there's the triangle image. I can see that one up.
Which one? Oh, you just saw it a second ago. The triangle image. Oh, there, right here. Yeah. Whoa. Hi. Smoke Monkey, thank you for that host. And everybody, hi. We're gonna get some questions here in a second. Smoke Monkey, hi. And everybody else that just came in. Hi, you guys. Skylias ignored the joke. No. I'm just trying to get through this so you guys can actually answer or ask your questions, and he can answer. Wow, words. But yeah, we've got, there's the triangle, there's the flat surface triangle, there's the sphere, and what that would be like. Yeah, I actually came up with some of these. Is there something and not nothing? Lawrence Krauss is really good at it. He has a really good book on that. But yeah, there you go. You talked about the recombination era. That was right there. But this was kind of breaking news. Where was it? Was this the BBC one? It is the BBC one. This is courtesy of Dodgy. I put this in my Discord today because we have a whole science area in my Discord. And this is the new image.
I'm not stepping away. I'm just going. I'll be right back.
You're fine.
My office got dark, and so I'm gonna.
You're good. Let's see.
Okay, I'm back. So you see my shiny head, but
Yeah, no, you're good. And so this is the new thing that just came out, right?
Yeah, so this is a map of the dark matter. So this is even though they use the same scale, like the same color scheme as the cosmic microwave background radiation measurements, this is actually not measuring the cosmic microwave background. This is measuring the dark matter density at different locations in the sky. So these are results from what's called the Dark Energy Survey. It's a survey that uses a very large camera. I mean, this camera is like 5 tons or something like that. It's a gigantic camera. And it's on a 4-meter telescope in Chile at Sierra Tololo, I think is the observatory. And
isn't Arecibo around there too?
So Arecibo's in Puerto Rico.
Puerto Rico, okay.
The ALMA,
right,
is the Atacama Large Millimeter Array.
Gotcha.
So that's the one that produces the images of like the rings of planet forming rings, that are planet forming disks where you can see the gaps where the planets are the planets that are forming are causing gaps in the rings. So that's in ALMA, and that's also in Chile.
Okay.
Because it's dry, it's tall, and it's in the southern hemisphere, which is good because we can't see it from the northern hemisphere because the Earth is round. So the Dark Energy Survey is a successor to the Sloan Digital Sky Survey. And one of the things that they can do is measure the distortion of different galaxies because of the presence of other galaxies. And so it's basically that gravitational lensing that showed evidence for dark matter. In this case, they're taking very small changes in the shapes of galaxies across large pieces of the sky in order to reconstruct the intervening dark matter across the whole sky. So it's not just like I'm measuring the mass of a given cluster of galaxies because of gravitational lensing. I'm actually measuring the shape of the blobs of dark matter across a huge chunk of the sky.
Wow.
And from that you can get improved measurements of the amount of dark matter that there is in the universe, and therefore improve our understanding of the cosmological parameters, like what's the actual percentage of dark matter, what's the actual percentage of dark energy, and so forth.
Yeah, and I didn't know that there was an international dark energy consortium. That's actually pretty cool. I didn't know that they actually did this kind of stuff here.
So that is probably the name of the science team for the Dark Energy Survey.
Mm-hmm.
And I imagine that there's like hundreds of people that are on that.
I would hope.
The science team. 400
scientists.
Authors on a paper, something like that.
400 scientists, and from 26 institutions in 7 countries. That's pretty interesting. And it's a 570 megapixel camera.
So it's slightly bigger than the one on my cell phone.
Yeah. That's so crazy. Okay, so I know a lot of people have been in here and they want to ask you questions. So
all right, should we do questions then?
Let's do questions.
I'm ready.
Yeah, guys, questions. Everybody's been.
I'm gonna consume some beverage.
So yeah, I'm having coffee. I'm extremely exhausted. Let's see what ones I can see here, or you can read them because you're gonna be. I might be a little bit delayed for you and then for stream. So.
Okay, so let's see. If I could just go backwards. Could the expansion of the universe cause the energy? We don't actually know. So this is from Tony Switchblade.
Yes.
We don't actually know the cause of the dark energy. We don't know if it's just a fundamental property of the universe itself, and so that would be the cosmological constant. If it's energy that's caused by vacuum fluctuations or vacuum perturbations to quantum fields. We don't know if it's the interaction between particles that have yet to be discovered that's causing the dark energy. So that would be like quintessence or something like that. So all we know is that right now the universe is going through a phase of accelerated expansion. Probably, if we really believe that quantum mechanics is the proper description, then it's due to some quantum mechanical force that's doing this. This would not be, it's unlikely that this is the first time that this has happened, because inflation, which we didn't talk about, we can talk about inflation some other time. Inflation is an example, if it happened, which the evidence is not convincing, but there's certainly large plausibility arguments for inflation happening. That was also a period of accelerated expansion in the early universe that eventually stopped. And so it may be that eventually the dark energy will stop. But right now we're going through a period of accelerated expansion. Let's see. Dark matter is an energy. Are you understanding that wrong? So this is too fat.
Too fat. Yep. Yep.
So dark matter is, so all matter has some energy. The difference is that dark matter interacts gravitationally and then therefore is attractive and causes things to collapse. Dark energy is has a different influence on stuff in the universe and therefore causes things to expand. But anything that has mass will have energy, because Einstein has showed that energy is E equals mc squared.
Mm-hmm.
So any object with mass is going to have some energy.
You have energy. Let's see. And Too Fat, don't worry, we're only censoring your name just because I'm going to put this on YouTube, and we have like a collection of, we'll be interviewing more people later on. And he's in my chat all the time and he hears me. I'm not always this way. I just respect people in education. And so don't worry, you guys are going to hear me be me, but this is out of respect to the guests for me. So just so you guys know.
So is the critical universe an example of a universe which no longer expands or collapses like a steady state universe? So if the universe is critical density and it's made only of matter, so the dark energy changes things a little bit. If the universe is just made with only stuff that gravitationally attracts, then the critical universe is a universe that expands forever but is bounded, meaning that it will continually get bigger. But the amount that it gets bigger gets less and less all the time, such that when you add everything up, you get a finite number. A good example would be if the universe is grows up to 0.9 and then, grows from 0.9 to 0.99 and then grows from 0.99 to 0.999, and then you add a 9 to the end of the digits all the time. The number is always getting bigger, but is getting bigger at a rate that's slower than, that's increasingly slow, so that you never actually pass 1. You're asymptotically or continuously approaching a finite number, even though you are slightly getting larger. So that's like a steady state universe, but it's a steady state universe in the infinite future. So dark energy could be infinite. Your guess is as good as mine about whether the dark energy is an infinite thing or not.
Mm-hmm.
Where does the additional dark energy contained in newly created space volume come from? We don't know what dark energy is. If it comes from just vacuum fluctuations, then whenever there's more space, there's vacuum fluctuations within that space. And so it would have the same property, the same energy density as the dark matter. I'm sorry, let me say it again. If you create more space, then the new space is going to have, if it comes from vacuum fluctuations, then the new space that you created will also have those vacuum fluctuations at the same density. And so every time you create new space, you create new dark energy, and then the system kind of runs away. That's what the dark energy actually is. And we don't really fundamentally know what dark energy is. So we don't actually know what properties it might have or what influence it might have in the distant future or in the past. We can only say kind of what it does right now.
Have you, or would you write a book?
I can show you some attempts. So I've started writing a book. I started writing one on exoplanets, but the editor, so one of our adjunct, or kind of affiliated faculty is Mario Livio, who worked at Space Telescope, and he has a few books. And he's given me some coaching on writing a book. I thought about, because my research history is significantly more varied than the average scientist. So I worked in neutrinos, I worked in Bose-Einstein condensation, I've worked in gravity, I've worked in particle cosmology, I've worked in exoplanets, and I've done airplane boarding. And that's kind of unusual. So I was thinking of writing a book that was basically like, if you have a distractible scientist and he kind of wanders his way through several subjects, what are those subjects? And then going into like what the science is behind each of those disciplines. That was kind of what I had as an idea for a book. What I do think I might do is, as I've been preparing for this class, I'm teaching a class this fall that I've never taught before, and I'm trying to relearn what I learned from my early physics, but relearn it in the way that I like to think about physics now.
Mm-hmm.
And I think I might try to make some good lectures about each of those subjects.
And on Twitch, maybe on Twitch, maybe.
So right now I'm doing lecture preparation on Twitch, and I've had several people, a lot of them coming from this stream, have kind of tuned in and helped out with a lot of stuff in terms of, I didn't understand that, and what about this question? But it's right now it's kind of me working through like my own thought process of how do I recast what pressure is in terms that I like to use instead of terms that the book likes to use. So it's a learning experience all around, including how do I keep track of all the different windows that I have open at once. Did the first generation of stars tend to last longer or shorter compared to stars now?
Well, that would depend on the mass.
It would depend on the mass. My suspicion is that they lasted shorter.
Yeah.
Because stars today will live for
long time.
Like the sun will live for 10 billion years.
Some will live longer than we know. We've never observed some of them dying, certain types of stars.
And so if the stars in the past live longer than that, then they should still be around.
Mm-hmm. If you got some,
easy to see.
If you got some red dwarf stars, they're probably still kicking around, yeah?
So there are certainly, it also would depend upon what's the mass distribution of the stars that you produce, because the lowest mass stars take the longest to live. They live the longest because they burn like sissies.
Yeah, they got that convection.
All right, let's see. If gravity is everywhere, there is matter. How do we know gravity doesn't cause matter? How do we know gravity doesn't cause matter?
Create matter, maybe?
So gravity is
maybe I could be wrong with what they're saying.
Is exchanged between objects that are affected by it. So, for example, an electric field is a force that exists between particles or objects that have electric charge. And so so that doesn't mean that the electric field creates the electric charge. Rather, the electric charge is a measure of the coupling between that object and the field that it creates. I'm sorry, between that object and the field that is created by that property. So an object has mass or energy. It will distort space-time. It will create a gravitational field. And mass is also the thing that couples to that field. But it's not the thing it's not the other way around. Mass causes gravity and not gravity causes mass. Mm-hmm. It's like saying electric charge causes photons. Photons don't cause electric charge.
Okay, yeah.
So if you want to make a photon, you take an electric charge and you wiggle it, and then you're making photons.
You wiggle it. So let's see.
Let's see. So I'm gonna.
I can kind of look at these. The question of the sphere is weird. Never thought.
Do we have a lot of dark energy near Earth or dark matter? The answer to that is no. At our location in the galaxy, we're right around the point where the density in stars and the density in dark matter are similar. So you can see how far apart the stars are in our neighborhood. There's roughly an equal mass in dark matter spread, as far as we know, spread uniformly between them. But that's not obvious either. It may be that dark matter clumps up on scales that are, like clumps up the same way the galaxies clump up. We don't know if the dark matter is a continuous and smooth halo or if it's a web like the galaxy structure web that we see. Let's see.
Photons have gravity. Photons are massless particles. So,
but they do have energy.
They
so
do have energy, right.
Photons do distort the shape of space-time as they pass through it.
Mm-hmm. So you get that light bending. Well, yeah, as it's moving through. Well, that's the gravitational lensing too. You can see that there. Because the topography of space is not flat. Space-time is a bumpy. Airplanes. Space-time is a bumpy. Mass creates a dip in the fabric of space-time. So it's not.
So there's the question, like, if the universe expanded from a single point, wouldn't it expand like a sphere? The answer is yes, but a sphere is a three-dimensional object. The universe is a three-dimensional object in a fixed coordinate system. The universe is a four-dimensional object in a changing coordinate system. And so it's harder to picture.
You got to just throw time in there,
Right. So it does expand uniformly. As far as we know, it expands uniformly in all directions. In fact, that's an assumption that goes into our, when I say a cosmological model, that's an assumption that goes into our theory, is that the universe is isotropic, meaning there's no preferred direction. The universe is the same in all directions. But you can imagine taking a sheet of paper and drawing a circle on it, and having stuff leave from the center of that circle towards the edge, and then you change the shape of the piece of paper in a different dimension. That's kind of what we're looking at here. So it would be expanding uniformly in all directions, but then the shape of direction is changing with time.
Right.
If you look at the same direction, the universe in all directions, do you see homogeneity? Yes. So homogeneity there are three fundamental assumptions that go into our models of the universe. One is that it's isotropic, meaning that there's no preferred direction. A consequence of the isotropy of the universe is that angular momentum is conserved.
And there's two different types or is there three different types of isotropy? I forget. That's just, yeah. So
it's isotropic in three dimensions, and so there's three conserved angular momenta.
Okay.
And then the universe is homogeneous, meaning that if you translate from one place to another, the laws of physics are the same.
Mm-hmm.
Like, there's no preferred location. So isotropic, it means that there's no preferred direction.
Right.
Homogeneous means that there's no preferred location. And a consequence of the universe being homogeneous is that you get conserved quantity called momenta. So momentum is conserved because the universe is translation invariant. The universe doesn't change as you go from one position to another. And then the third thing is that that we're not special. Is the third. I mean, we're all special snowflakes as individuals, but the Earth, there's nothing particularly special about the location of the sun in the universe.
So you guys hear that? Sorry, there's Twitch chat gives words all kinds of fun things, but at chat we are special snowflakes. No, it's good, but yeah, no, that's wait, let's see. Delicious Hawaiian treat. Biology gets pretty mind blowing when you see how complex yet necessary the reaction. Yep.
Did the Bose-Einstein condensation work have any astrophysical bent? No, that was as I was an undergraduate. So when I was an undergraduate, that's when the Nobel Prize was awarded for Bose-Einstein condensation. So Bose-Einstein condensation is a unusual quantum phenomenon that happens when you cool particles down to the point where they eventually all occupy the same state. And so you can have a collection of like a million particles, or a million atoms that behave as a single atom. So that's Bose-Einstein condensate. That Nobel Prize was awarded when I was an undergraduate, and we worked for a while on reproducing their result. Because once a graduate student does it, then it gets refined fairly quickly. And now Bose-Einstein condensation is a daily thing. It happens all the time. Let's see.
There's a really good one. I have a serious question. How can we measure the microwave background faster than what radio waves can travel at light speed via the Colby satellite?
Okay, where's this one?
It's down at the bottom, like Taco Cat
Oh wow, I'm
Supreme.
falling behind.
Oh, you're okay. Like we can get a. I was just looking at some of the other ones. There's some.
Uh, so, all right, I still can't see it.
It's at the very, very, very
Radio,
bottom. I mean, not the
radio.
very, very bottom. I was telling Tony he can't leave. And there's King's Throne. Hey, it's Taco Cat says, I have a serious question. How can we measure the microwave background faster than what radio waves can travel at light speed via the Colby satellite?
How can we measure the microwave background faster than what radio waves can travel? So we can't. Rather, what happened at the time of recombination. So recombination is the phase transition that took us from the transparent universe to the opaque. I'm sorry, from the opaque universe to the transparent universe that produced the cosmic microwave background. So the question is, how do we measure it faster than they can arrive? And the answer is we don't. Rather, what happened was this was a phase transition. This transition that produced the cosmic microwave background happened everywhere at once. And so every second that goes by, you are seeing the cosmic microwave background radiation 1 second further distant, further away from us. So the cosmic microwave background that you see right now is slightly different than the cosmic microwave background that you see right now because it's light coming from a different part of the universe. Now, the universe is so big that you would have to watch the cosmic microwave background over a very long time in order to get a different picture than what we observe today. So when we observe it over the course of 5 years, the smallest structure that we would be able to resolve is something that's 5 light years in size. Mm-hmm. So Kobe, for example, flew for I think it was about 5 years, but certainly WMAP and Planck are around 5, maybe 10 years in total duration. And so they would get fuzzy, the image would get blurry once you resolve length scales that are of order 10 light years. But the typical size of the features that they see are actually like hundreds of thousands or millions of light years across. And so we'd have to put a satellite up that would observe things for 1 million years in order to see basically the fact that we're not actually seeing the same photon all the time. We're seeing light coming from different directions at once. Mm-hmm. I hope that explains what's going on. Let's see. So the star that is simultaneously killing itself and creating itself is called Eta Carina.
And I'll show you guys that on Space Engine when we're done here. I'll show you Eta Carina.
Let's see. Is there a highlight section where we can recap this?
Yeah, I'll be making a highlighted VOD.
That's above my pay grade.
Wait, is he not talking about me just sectioning this off? I think maybe.
The microwave background is cooling slowly. Is that right? So the answer to that question is yes, the microwave background that we observe is cooling as a function of time. We won't be able to see changes in temperature in our lifetime because we're talking billions of years instead of hundreds of years or like decades. And so it would be, but it is true that because the universe is continuing to expand, the photons that are coming to us from that epoch in the distant past are being stretched out slightly more, and therefore the temperature is cooler. So in this case, temperature is defined by what is the average wavelength of the light that's coming to us. And so as that wavelength gets stretched out, the temperature drops.
Yeah, so I'm gonna actually say like no more questions after this point because I don't want him to have to stay here forever. But you got one that says before. Well, no, that's not a question.
Is there still a disagreement between the effective number of neutrino species from nuclear synthesis and CMB? I believe. Okay, so this is from Circinus. I believe that the disagreement is still there. that that there are either 3 or 4 neutrino species. And in fact, as dark matter experiments are ruling out possible dark matter candidates, like certain kinds of WIMP candidate for dark matter. Okay, as dark matter detection experiments are ruling out certain WIMPs or certain parameters for WIMP particles, the sterile neutrino, which is a type of neutrino, is kind of seeing a resurgence in plausibility. It's starting to suggest that maybe WIMPs aren't some supersymmetry product or something like that, but maybe we should start looking at this disagreement between the number of neutrino species that you get from studying cosmology and what you get from particle physics. And so, yes, that disagreement, I think, is still there. It may go away as we continue to refine our measurements, but the last time I checked, it was still there.
And I think that might, wait. You got one from Azir. Hi, Azir. Is there an estimate for what percentage of matter in the universe is contained in black holes?
That is a good.
That's a good question.
Very good question. The answer to that question is we don't know.
That means it's a good question.
What we can say is in the galaxy. So it's not an obvious conclusion that the dark matter that makes galaxy clusters is the same as the dark matter that makes galaxies themselves.
Right. So
there could be different kinds of dark matter. If you had black holes in the galaxy, so if the galactic dark matter is made out of black holes or other massive compact halo objects, versus instead of a weakly interacting massive particle, see how clever scientists are? If the dark matter is made out of, we know that the dark matter is not made out of like compact planets or collapsed stars or things like that, because the Big Bang nucleosynthesis tells us that it can't be regular matter. It's got to be something else. It could be black holes. So if it is black holes, then the question is, what is the mass of these black holes? And we can place constraints on the mass of the black holes by looking for gravitational lensing effects. As you look towards the center of the galaxy, if the dark matter is made out of black holes, as the black holes pass along the line of sight, it will distort the shapes and the brightness of distant stars. And so it was shown that these black holes, either there's a small range where they could be like 1 to 10 solar masses, and then they would have to be small, like Earth-sized, Earth mass objects. But they really can't be anything in between. So there's small windows where it could possibly be black holes. The dark matter could possibly be black holes, but the available, but the mass of those black holes has been excluded to a large extent, and there's only small windows of still plausible versions or still plausible masses for these things. So the best answer to that question, I guess, would be it's possible but unlikely given the amount of space that's left to find them.
All right, I think we can, I think that, is this channel? Yes. And so we have another astronomy major. Maddie I major in astronomy. I love this. Good. Because we're trying, so again, since everybody's in here, anybody that has joined recently, we have, if you're going to TwitchCon, we have a panel. Dr. Steffen and I are going to be on for education for Twitch. Starting a new thing here. We're trying to, so, that is kind of what we're pioneering or trying to here. So there's a vote. If you guys do ! Vote, you can go place your vote to say that you actually like this stuff. Now this is a little technical. I do space streams too, where we just kind of explore space. We're going to do a little bit of that after Dr. Steffen leaves. And then we're going to have on August 14th, you guys will be seeing this on my Twitter. I'm not really a social media person, but I have an Instagram and Twitter, and those are just two not even related things. Twitter is more for, I send out a lot of science news and updates on things that are going on. And so we have the woman that discovered Tabby's star on August 14th. So at 6 p.m. Mountain Daylight Time. And I will be making sure that everybody knows about that. And you can join my Discord too. We have a bunch of news in there as well. If you want to, you don't have to. I think.
So do we declare victory for tonight?
I think we did. I think that was awesome. And I'm just going to take them around space for a bit, and you can yell at me about certain things, and we can go and look at those things too.
So then, so we have that coming up in 10 days, and then we're going to try out that format, and we'll see who else we can get. A couple people that, I have some ideas of people to invite next, to see if I can track down next for.
Yeah. So we're gonna have some more people in here, being interviewed. He's awesome because he knows a lot of people, obviously being in this industry, and I'm just, a lowly computer science graduate advocating science on Twitch and education actually as a whole.
Yeah, and I will be. I need to get more information to you for the tour of JPL.
Right, and that's another thing with TwitchCon. I'm basically landing, and we're going to be going to JPL in Pasadena, and hopefully I can take you guys with me. I think I'll be able to with the NASA Media badge and certain restrictions, whatever. But I'll be streaming that live, and hopefully. We're doing a few test runs of the IRL stuff, and I'm trying to figure that out. But I haven't tried it on my phone solely. I will be doing that alone. But I'm not done, guys. I'm not done. But we want to free him up because he's been here for 2 hours. Or not 2 hours full, but about 2 hours. So but these are good.
Thank you. Yeah, we'll talk to you later.
Yeah, and guys, here's his channel. I'm going to have him, Mod, you could post it. Yes, and thank you so much, Dr. Steffen. I appreciate your time. Say goodbye to Dr. Steffen, guys.
All right.
All right, see you later.
Thanks for your time.
Thanks.
Oh.
Hi. I just totally... How are you guys doing? Okay, I'm going to not move my Spotify playlist over there. I'm still totally doing the window capture. Or not window, that's my monitor capture. Let's not do that. Display capture off. And let's go... I need to go grab some water real quick. My water's not cold, and... I'm not that fancy, guys. So give me a second. And we're going to go do a little bit more space stuff. Hi, music colliding with one another. So give me 1 second, guys. I will be back, and we'll go into the space program that I use. That's free for now. And I'll be right back, guys. Right back.